In this screencast, I'm going to show you a method for simple linear regression using least square estimators, and then we're going to compare this to the regression output in Excel. Simple linear regression is the simplest model. Y equals some intercept, beta naught plus beta 1, which is our slope, times x plus some sort of error term, random error. The regressor variable is x. Capital Y is known as our response variable, and our intercept is beta naught. Our slope is beta 1, and our epsilon represents a random error term. This has mean 0 and variance sigma squared. If we plotted a bunch of experimental data points, these blue dots, and we are trying to create this blue line of best fit, each of our experimental data points represented by index I is going to have an error term. So for example, this one's going to have an error term, maybe epsilon of 2. We wish to find the line of best fit, and to do this, we want to try to minimize the overall squares of these error terms. This is known as the least squares, or L. So L is just the sum of all these epsilons squared. If we solve for epsilon in this equation up here, that'd be yi minus beta naught minus beta 1 xi, and we square that. So this is how we can find the least squares, or L. We wish to minimize L to minimize the overall error. Since the model is linear in beta naught and beta 1, this can be solved using calculus. So we can take the partial derivative of L with respect to beta naught and beta 1, and we get the following. It's beyond the scope of this class of how we get this, but we have these beta naught hat and beta 1 hat are estimators of our true intercept and slope. If you perform this calculus, this yields two linear algebraic equations in beta naught hat and beta 1 hat. These are called the normal equations. And again, it's entirely fine if you are not following how these are derived. It's sort of beyond the scope. If we solve the normal equations for beta naught and beta 1 explicitly, we get the following. You first need to calculate beta 1 hat. This is just the product of xi minus x bar times yi minus y bar for each of your data points. And then you sum that, this is known as sxy, divided by the sum squared of xi minus x bar for all of your data points. And this denominator is known as sxx. Once you have beta 1 hat, that's your estimate for the slope, you can plug it into this equation up here. We know x bar, that's your sample average. We know y bar, that's the average of your output. And then you can calculate your estimate for the intercept. These are the parameter values that give a straight line that minimizes the sum of squares criterion. So let's work with some data. We have temperature as our x variable, our regressor variable. We have porosity of zirconia fine powder. Let's go ahead and do this in Excel. We're going to make a quick plot. We're going to run the regression tool, and then we're going to calculate by hand, in Excel using these equations to see if we get the same thing. And this will kind of demonstrate how Excel calculates beta naught and beta 1, our slope and intercept parameters in the regression output. So I've got the data here. This is in a file called zirconiadata.xlsx. We have temperature and porosity. You guys know how to put together a linear regression model in Excel using the regression tool. And when we do that, you get the following. Our intercept is about 70.1. Our slope is negative 0.041. And we've got all this other stuff in the regression output. You're going to learn in this class basically everything in this output. In this screencast, you're going to learn how to calculate these green highlighted cells in the regression output. So let's go ahead and calculate our estimates for the slope and intercept. That's beta 1 hat and beta naught hat. First, we need to calculate sxy and sxx. We need to calculate xi minus x bar for each of our experimental data points. We need to calculate yi minus y bar for each of our data points. I've already calculated x bar here, the average temperature, that's named x bar. The average porosity, that's named y bar. So to calculate this, I just subtract from each of my data points x bar. I do the same thing for yi minus y bar. That's my yi minus y bar. We can drag these down for all of our data points, and if we summed the product of these two columns, that would be SXY. So let's go ahead and do that. SXY, there's a nifty formula in Excel called the sum product of two arrays. It multiplies the corresponding elements of those two vectors and then adds them. So this is a nice way that we can calculate SXY. SXX is just the sum squared of our xi minus x bar column. So we're going to square each of those elements and then sum. And so we end up with SXX of 280,000. Now that we have SXY and SXX, we can calculate beta 1. Beta 1 is just the ratio of SXY to SXX, and that's equal to negative 0.0406. And that's exactly what we got here in the regression output. Now that we have beta 1, we can use this top equation here to calculate the intercept. That's equal to y bar minus beta 1 times x bar, and that's equal to 70.07. Again, that's what we got in the regression output. So we can use our experimental data to estimate the line of best fit based upon these equations for the slope and intercept. So now let's talk about model adequacy. How good is the model? Each pair of observations satisfies the relationship here. We have a difference between the prediction. The prediction is y hat, and this is known as the residual. Each experimental data point is going to have a residual. We will use the residuals to provide information about the adequacy of the model. Let's first calculate something known as the residual sum of squares. That's SSE, sum squared of the error. This is just a sum squared of all of the residuals. So let's go ahead and use this equation up here for the sum squared of the error sum of squares. We need to calculate a new column here. That's going to be y minus y hat. But we first need a prediction. That's our model prediction, y hat. Y hat is just going to be the equation for the line that we came up with, which is beta naught, that's our intercept, plus beta 1, that's our slope, times the corresponding x for that data point, which is over here for the first one, 1100. That means our prediction based upon a straight line is going to be 25. We can now calculate y minus y hat, and that's also known as residual. We take our porosity minus our y hat, and we do that for each of our experimental data points. These then are the residuals of our experimental data. For SSE, we can simply use the sum squared function in Excel, take the sum squared of each of our residuals. We're going to square each of those and sum, and that gives us SSE of 60.81. You notice that in the regression output, here in the middle in this ANOVA table, there's a residual sum of squared denoted by the SS, and that's exactly what we just calculated. We can use our residual sum of squared, SSE, to get an estimate for the variance of our output, sigma squared. So sigma squared hat, that's an estimate, is just SSE divided by n minus 2. We have a 2 here because this is the number of parameters in our model. We have beta naught and beta 1. We can use that estimate for the variance in a series of equations here. It's not important how these are derived, but the variance of our intercept is given by this formula. The variance of our slope is given by this formula. We've already calculated SXX. Using these estimates of the variance, we can define the standard error estimates for the estimators, beta naught and beta 1. If you don't follow this, that's entirely fine. The important finding here, though, is that the standard error, denoted by SE, of our slope is given by this formula, and we have a standard error of our intercept given by this formula. These can be used to perform hypothesis tests and calculate confidence intervals on the slope and intercept. So let's go ahead and calculate these in Excel. Let's first calculate sigma hat. We're going to use this equation up here, and that's just the square root of SSE, our residual sum of squared, divided by n minus 2. And we end up with a sigma hat of 3.49. This is also known as just the standard error. Our regression output provides this for us up here in the standard error box, 3.49, and that's what we just calculated. Now that we have sigma hat, we can calculate the standard error of beta naught and the standard error of beta 1. Let's just go ahead and name this real quick, sigma hat. We can use these formulas here to calculate the standard error of our slope and intercept. So I've punched in the formula there for the standard error on our intercept, which we get about 9.32. This is shown in the standard error here for the intercept in our regression output. We can type in the formula here for the standard error on our slope, and we end up with 0.006591. And that's also shown here in our regression output, the standard error of the slope. In the next screencast, I'm going to show you how we can use the standard error on our slope and intercept to calculate test statistics, p-values, and 95% confidence intervals on the slope and intercept of our equation for the line.